Okay, folks, we're going to go ahead and get started. Can folks hear me okay? Yeah? Okay. All right, so a couple announcements before we begin today. Project Zero was due Friday, so if you still plan to do Project Zero, go ahead and get it done quickly. Optional, as well as Homework Zero was also optional. That's due tonight. Homework 1, I believe, is out, so you can find that on the website. And that's due next Tuesday. And Project 1 will be due the following Friday, so Friday of next week. If you had a chance to scan this QR code, we'll do attendance later in the lecture, but there will be another QR code later. So I'm just going to move forwards. Today is about informed search. It was originally going to be Michael. Michael's sick, so I'm filling in for Michael today. But informed search is basically like last time we looked at uninformed search, and we'll kind of review a little bit of what that looks like in this class. But informed search is like, why are we spending time searching stuff that we don't need to search, right? What if we had a little bit of, like, what if we had this device that we could carry around in our mazes with us, or in our planning problems, that could tell us whether we're getting closer to the goal or farther away, and then we can use this almost like a compass to make sure that we're going in the right direction in our search. So we're going to talk about a few different concepts. We're going to talk about heuristics, which is really this little device. This is like how you're going to tell whether you're getting closer to the goal or not. We're going to look at greedy search, which exploits that heuristic and just goes straight for the goal. A-star search, which is a little bit smarter about it. And then graph search, hopefully we'll have time for today, which is what you do when you have loops in your graph and then you don't want to sort of get stuck searching the same states over and over again. So yeah, before we begin, questions from last time on search? Okay, and if they come up during the lecture, that's totally fine too. So just like make a big wave at me so that I can see you properly. Right. So just to recap, search was this idea that like we have a goal that we want to try to achieve, and we have a model of the world, which is well, to get into it, we have states and we have actions and we have some successor function that tells us what happens if we execute these actions. Actions might have costs. And so we went through and we said, for this particular planning problem, here are the states and here are the actions and here's the successor function and here's the costs. We also have to have a start state, which tells us where do we begin searching, and then we have to have a goal test, a goal condition. Sometimes this is a single state, or sometimes this could be a collection of states or some condition, a function that we can pass a state to, and it'll tell us whether we've satisfied our goal or not. But when we're doing all this, we have to kind of remember that we're wearing two hats. The first hat that we're wearing is the problem designer hat. This is like, we look at the complexity of the world, and it has, all this information in it, and we want to sort of distill that into the core of the planning problem. So the first hat is the planning problem designer hat. And then the second hat is the search algorithm designer hat. And this says, you hand me a planning problem and make sure that it's specified in the right format, and I will give you an algorithm that will solve that planning problem. So these are two hats. The first hat is, how do we model the world as a planning problem? And the second hat is, how do we solve planning problems once they're appropriately modeled? So that first piece is the search problem. We talked about that already. And then part of the algorithms is we need a representation for going through the process of search. And so we talked about visualizing that as a graph, and we talked about visualizing that as a tree. And if you visualize it as a tree, then the nodes represent plans for getting to particular states. And so we had this issue that could come up, which is that we might see states in the tree more than once, because that represents different ways, different plans of reaching those states. And some of those plans might be better than others. Right, and these plans can have costs. Sometimes we assume the costs are all one, and sometimes we assume the costs are different. It depends on the planning problem. And then when we're doing the algorithm, this will systematically build a search tree, and then we're going to keep track of nodes that we have yet to search in what we call a fringe. There's a very good chance that I'm going to end up calling it the frontier today, because that's the way that I learned it. So fringe equals frontier. And we're going to choose an ordering of this fringe. These are the unexplored nodes. And the different orderings give us different search algorithms. So if we just go level by level in our search tree, that's going to correspond to breadth first search. If we go down the search tree and then come back up and then go down all the way, that's depth first search. We also looked at uniform cost search, which we will review a bit today. And we talked about optimal plans and optimal search algorithms, which is when we find an optimal plan with our algorithm. These are the least cost plans. And so today we'll prove that one of these algorithms that we'll look at is actually optimal. So yeah, we've looked at like the maze navigation, and we've looked at the Pac-Man environment. And so you might be thinking like, okay, 2D navigation is pretty much what you use search for. But let's think of, I mean, this is a very general concept, this idea of AI planning. So there are lots of planning problems that don't map onto 2D navigation that we can also look at. And one of those is this kind of fun little pancake problem. So imagine that this is a stack of 4 pancakes and that I have a spatula. And this is not a particularly appetizing stack of pancakes. Why is that? Because pancakes need to go from top to bottom, they need to get bigger, right? Because otherwise you pour the syrup on the top and it's not going to trickle down the sides. You're going to miss a couple of pancakes with your syrup. So this is not the right way to arrange your pancakes. So if we have this pancake problem and we have this spatula, we can use this spatula to flip some of the pancakes around. And so doing that is going to cause the arrangement to change. So maybe if we put this spatula just beneath the second pancake, we could flip it, and then the top 2 pancakes will flip over. And so this is like a new state of our planning problem, right? So we have this world, it's pancakes world, and we want to model that as a planning problem. So now we have to think about like, what are the states going to be? The states could be configurations of these pancake stacks. And then what are the actions going to be? It's going to be like flipping pancakes from one configuration to another. And we could do that at any level, right? We could do it for the top 2, or we could do it for the top 3. That looks like a pretty appetizing stack of pancakes. That's kind of, maybe that's our goal, right? We want it to look like that. And then we could flip all 4 of them, and that kind of gets us to here. Does that make sense as a different type of planning problem? This still works. Everything still works. We can give costs to these actions. Maybe it costs more to flip more pancakes over. I don't know. Maybe you have to be stronger, right? Yeah, and then we could make up some kind of plan from some initial state to get to some goal state. Here the plan would cost us 1 action. I don't know how much that particular action will cost. Maybe it costs us 3 because we flipped 3 pancakes. Makes sense as a concept? Like we can use this for stuff besides 2D search, 2D pathfinding. Seeing some blank stares. You might be thinking, who in their right mind would actually care about flipping pancakes as a planning problem? Maybe this is the picture in your head. You think this is really kind of a silly thing to do. But there's this one paper by a William H. Gates. I don't know like what he went on to do. Maybe he went on to like found some important pancake business. But yeah, he was interested in this problem. So maybe you should be too. Right. So we can look at this planning problem the same way we did before. We have like a graph. We put all of the states that we have for this planning problem into this graph. Each one of the nodes is a particular state of the world, and then the actions are the edges between those, and we've put numbers on them to represent the costs of moving between these states. So imagine we're at this state, right? And so we can take 2 actions from this state. We can flip the top 2, and that'll take us here. We can flip maybe there should be another edge here if we flip all 4, but yeah, if we go this way, then we flip the top 3, and that gets us to this state. And so we've connected all these nodes together, and this is our sort of planning graph. Costs are weights along the edges. So here's an algorithm. I'm not going to take you through the algorithm, but this is sort of pseudocode for how you would do tree search. We talked about tree search last time. Essentially, the idea is you're going to start with some starting state. That's this one. And then you're going to add that to your fringe. Then you're going to take it off the fringe, because there's only one thing on the fringe. That's what do we still have to explore. So it's in the fringe, and then we say, all right, let's take it off the fringe, put its successors into the tree. Those are its successors. Maybe we take these 3 actions, and those are the next states. Now, These might have costs associated with them. These are now our new fringe. When we get to here, we're going to pick one of these, and this is where tree search comes in, right? So we have some strategy for expanding the fringe. And this strategy could be breadth first search, it could be depth first search, it could be uniform cost search, and it could be any of the things that we're going to talk about in this lecture, which will all use heuristics. But we pick one of these nodes, we expand the fringe, and then we pick another one, we expand the fringe again, and that's sort of how tree search works. Questions on this part? It's all making kind of some sense? Nice. Right, so uniform cost search we looked at last time, and I just want to kind of give you a diagram of what this looks like in Pac-Man. Let's say that Pac-Man starts here and wants to get to this dot. So this is just the go to a particular location problem. And what we see is, so we've colored the hallways red, and what the colors mean is like red is you search those states first, and then sort of the darker colors, the grayish colors, you search those ones towards the end of your search. And so what you see is that uniform cost search, it starts out close to Pac-Man and kind of just expands out in all directions, kind of equal amounts, right? Because uniform cost search, first what it does is it searches all states that are cost 1 to reach, right? So that's just all these states. And then it searches all the states that are cost 2 to reach, right? And there's only 3 of those. And then it keeps going out, cost 3. And before it searches any states that are cost 4, it has to search all the states that are 3 steps away, and so on. So this feels like it's a little wasteful, right? Because the direction of the goal is down here. So if you just knew that this is your goal, and you knew that this is your starting state, and you could somehow figure out that this is the direction you want to travel in, it's kind of wasteful to go all the way over here, to go all the way up here. Like, we're kind of wasting some compute on searching stuff that we know is not really in the direction of what we want to do. And so that motivates basically all of today's lecture, which is, what if we had some way of figuring out if we're getting closer to the goal or not, right? Can we use a meter like this to help us guide the search and prune some of these less interesting branches out of our search tree? So these are called heuristics. And a heuristic, we'll define that formally in this class. It's just a function. It takes a state as its input, so a state of the world, something in our planning graph. We send this state into our function, and out comes a real number. And that real number just tells us how good is that state. Is it close to the goal? How many steps away is it from the goal? So this is some estimate of how close a particular state is to the goal. This is obviously designed for a particular search problem, because I can't tell you how many steps you are away from your goal in a different search problem if my heuristic is about, this goal. So this is goal specific, it's problem specific, and there's a lot of work that goes into figuring out what is a good heuristic. We'll talk about some of that. But the basic concept is this. We hook our AI planning agent up to this heuristitron, this heuristic, which takes in a state, and it outputs whether you're close to the goal or not. How close are you? And so this one, it's pretty pessimistic because it's pretty far away from the goal, so we're kind of down here. And in this state, the robot has woken up, and now we're like, oh, that actually, maybe we should start paying attention. We're getting close to the goal, right? So this is how the heuristic works. The heuristic tells you how many steps away are you from the goal. And we can apply this to Pac-Man. We can develop a heuristic for Pac-Man. And remember, we're trying to get down here to this bottom left corner state. And so we could add a heuristic. Can anyone think of like what might be a good heuristic? How do you estimate the distance to the goal here? Yeah. Euclidean distance. Yeah, good. Nice. So that looks like this. And I sort of gave away another option. But yeah, Euclidean distance. It just says like, how close are we in two-dimensional space to that point? And this is good. This will give you a sense of which direction you want to go in. And this is a vector, so it's pointing. It's like a compass. Okay, what else? We could also, I just gave it away. So there's also Manhattan distance, right? So folks that have lived in New York City or visited, you know that there's all these city blocks and you can't go through them diagonally. You can only go around them. And so everything is either north-south or east-west. Technically, Manhattan is like a few degrees off from that. So there's like Manhattan north, but that's not important. You have to go 10 blocks west and 5 blocks south in order to get to this dot. And because Pac-Man only allows you to travel north, south, east, west, that's like a totally fine heuristic to use as well. So this will get you there as well, because you have to go all the way east, or sorry, all the way west, and then you have to go all the way south in order to get to this dot. And this is basically saying, if I didn't have to think about any of the walls, how quickly could I get there? So this is just an estimate. Of course, like the true number is going to have to take into effect all these walls, but then in order to figure out how far away you are, you have to actually solve the plan. So this is really just an estimate to help guide us. We can also apply heuristics to this like Romania navigation problem, right? Remember we were trying to get from Arad, which is up here, all the way over to Bucharest. And so here's a bunch of cities. These are all the cities in this graph. And then here's a bunch of straight line distances. And this whole thing, this red box here, is our heuristic function. It takes in a state. The state might be Arad, right? It could be Arad. Arad's at the top. And it will give us a real number. And that real number says how much do I estimate it's going to cost me to get to the goal from this state. And so we see 366 kilometers. And I think that's like the straight line distance from Arad to Bucharest. And this basically says, don't worry about roads, don't worry about mountains, don't worry about trees. You can just go through directly, straight line, get from Arad to Bucharest. So this is also a totally fine heuristic function. We could add one for this pancakes example too. We could say maybe the number of the largest, like the index of the largest pancake could be our heuristic. And so the index of the largest pancake that's still out of place, and we could add these heuristic values to our graph. And this may or may not make intuitive sense to you. Maybe you don't have an intuitive feel for pancakes yet, but this will work, right? Because what is it doing? Notice how the states that are farther away from the goal state have larger numbers, and as we get kind of closer to the goal state, they have sort of smaller numbers. So this has the right feel of a function that's telling us if we're going in the right direction. So what do we do with a heuristic function? Well, one thing that we could do is just try to minimize it, right? Greedy search directly to the thing that we think is good. So if we think that this is a good state, we just go directly there, follow this heuristic. The minimum heuristic value is the one we're going to search first. So we're going to expand the node that seems the closest. What would that look like for this Romania example? Well, we start with Arad. Arad has a heuristic value of 366. And then we're going to expand Arad, and we get its successors. So we see Sibiu has 253 for its heuristic value, and then we have these other cities which have higher heuristic values. So we're going to expand Sibiu first. Remember, we have to come up with a way to decide which of these nodes on our fringe do we want to expand first. And now we're just saying the lowest heuristic value wins. So we expand Sibiu, we get a bunch of states. Notice that Arad is still there. Why do we have Arad in our search tree? We already were at Arad. We have it because that's a path that we might take, right? We can go from Arad to Sibiu. It's kind of a silly path, but we could go back to Arad from there, and maybe we need to think about that. So if we're here, we're at Arad, we go to Sibiu, we go back to Arad, and our heuristic value returns to its value from before, because the heuristic doesn't care about the path. It just says for a given state, how far away from the goal am I? But that's not the lowest cost. So that's not the one that we're going to expand first. We're going to first look at this one, Fagaris, which has 176 as its heuristic cost. So we'll expand that, and we see that the two nodes, we go back to Sibiu or we go to Bucharest, right? And Bucharest has a heuristic cost of 0. Why does it have a heuristic cost of 0? Why does Bucharest have a heuristic cost of 0? Yeah. Because it's the goal, right? It's a heuristic that's estimating the cost to the goal. We're at the goal. So the heuristic value should be 0. So here we go. We found the goal. The heuristic says we're done. We're done. That's great. We found a plan. Anything wrong with that plan? It might be kind of hard to see on this map here, but there is a shorter path. We could go 99 through Figueras and then 211. What is that? Do math on the spot here. That's 310. Is that right? Versus we could go 80, 97, 101. That's going to be less. I'm not going to embarrass myself by doing more math. So that'll be less. So we could have gone through Sibiu to this other city, and then we went through this second city and then get to Bucharest, and that would be faster. Why didn't we do that? We didn't do that because Figueras had the lowest cost. We could have gone here. This had a low cost also, but this is the lowest cost, and we're doing greedy search, so we're just trying to get as close to the goal as possible, as fast as we can, and we just believe our heuristic, whatever it tells us, even though it's just an estimate, okay? So we expand this one, we get to Bucharest, we say we're done, we declare victory, and there might have been a better path. Yes? Where does the 176 come from? Yeah, so the 176, the one that we saw here, this is coming from our heuristic function, which either we had to design for our planning problem or someone handed it to us when they handed us the planning problem. So this is just a function. It takes in a state, it gives us a real number, it's customized to a particular planning problem, and someone hands us that, or some expert designed that for us. Oh, you're asking how they got it? Yeah. Yeah, so the way that they probably got this heuristic was like it's the straight line distance from, let's say, Figueras to Bucharest, right? So, and it's just an estimate. So you're like, well, why isn't it 211? That's the straight line distance. Well, that's a straight line distance over the roads you have to take from Figueras to Bucharest. But if you didn't, if you could go like as the crow flies, right? Like then you could maybe get there in 176 kilometers. Make sense? Okay, more questions, yeah. Yeah, so that's a great question. We're going to have to keep track of what we've seen. Hopefully we'll have time for graph search towards the end, but we'll discuss that, yeah.
If you can go like just straight line, why are you even stopping in cities?
Yeah, so you can't really go in a straight line, can you? I mean, do you know how to get from...
What's the point of the heuristic?
The heuristic is just an estimate. It's really to guide our search, to say like, what is a useful direction to go in? So the heuristic is just an estimate. We can trust it as much as we care to trust it. But yeah, you're starting to see that like it can sometimes lead us down the wrong path. We might want to hedge our bets against this heuristic because it's only an estimate. Yeah.
How do you measure if a heuristic is the most accurate heuristic that you could use, like a good heuristic to use?
Yeah, that's a good question. We should have time to talk about that towards the end. The values of what? The heuristic values? Yeah, so sometimes you can design a heuristic for a particular problem by looking at like relaxations of that problem. We'll get into that sort of later in the class. Other questions? Yes? Right. Yeah, why can't we use the actual costs of the roads? So that's a fair question. What if our heuristic was just equal to the cost? Is that kind of what you're asking? So we'll answer that question later in the class too. Yeah.
Wouldn't that just be solving the problem?
Okay, so this is a preview, yeah. So if we do that, we're just going to be solving the planning problem if we use the actual cost. So how can we, yeah, so maybe I'll give it away now. So if we use as our heuristic the actual cost to reach the goal from a given state, well, in order to know what the actual cost is, there needs to be the optimal plan from that particular state to the goal. Well, we're trying to use this heuristic to help us find the optimal plan. So we can't use the optimal plan in finding the optimal plan. It's like a circle, yeah. Well, so we might know the action costs, but we don't know necessarily what the total from here to the goal is by the optimal route. Yeah. Yeah.
So we'd have to redesign the heuristic if we change the goal and like starting
If we change the goal, we would have to redesign the heuristic. What about the starting point? Do we have to change the heuristic for the starting point? Well, the heuristic takes in any state in our problem, right? So it doesn't have to be the starting state. It could be any state in our problem, and it'll output the distance to the goal. So if the starting state changes, that's okay. We can keep the same heuristic. Yeah. More questions? Yes?
But does greedy search only look like one step ahead every time it runs?
Greedy search is looking at the nodes in the fringe. So we'll get into what it looks like, yeah. More questions? All right, let's do it. All right, so let's keep going. We saw what can go wrong. Greedy search can give us a pile of junk for a plan instead of the diamonds that we thought we were going to get. That's kind of annoying. Can we do better than that? Maybe. Here's another picture of greedy search. Greedy search is basically, can folks see the gray this time? Is it like a bit easier to see? Okay, nice. So the greedy search is basically saying, I think the goal is that way. Let's go that way. Let's just go directly there, right? So we tunnel through the search tree directly in the path towards where we think the goal is. It might take us down the wrong path. Worst case, this is like badly guided depth-first search. We're just tunneling in. We think that we're going in a reasonable direction. Turns out maybe not. Who knows? Badly guided DFS. So we might actually end up exploring all this stuff before we even find the goal, which would be really annoying. Can we do better than that? Well, okay, so here's a demo of what this looks like in a empty maze, right? So green is the start, red is the goal. And greedy search, if we run this video, it looks like this. Instantly finds the optimal plan. That's great. Yeah, but what happens if it's a slightly harder problem? Like what happens if it's this Pac-Man problem, right? I've already started it. So we're here, we want to get to the goal. What does greedy search do? Greedy search looks like this. Okay, so first it goes this way. The heuristic says the goal is this way. Let's go this way, right? So the first three nodes are 1, 2, 3. Those are the places that we could go. And greedy search says, yeah, this one has the lowest heuristic. Let's open that. And then from there we have this one, and we have the starting state again. And the heuristic says, this one's the lowest heuristic, so let's do that. And then you just keep going. You come down this way, you come over here, and then you get to here, and then you have this one and this one. So you sort of alternate expanding these things. And you go backwards, and now you're going this way. At no point do you ever reach this, because all of these nodes have lower heuristic cost than either of these two nodes. So these ones will just remain on your fringe, on your frontier for the rest of the search. Greedy is going to get down to here. It's going to declare victory. It's a suboptimal plan because you could have gone around this and avoided this whole annoying wall. And so we could have found a shorter path. But that's how greedy would work with walls. A-star search is going to be a little bit more clever, and hopefully it's going to find the more optimal gems in the bottom of this search hill, right? So if we're a bit more clever about it, maybe we can find optimal solutions. And we can think about this as like, okay, so we're going to contrast the behavior of a planning algorithm from last time with a planning algorithm from this time. And these are our two characters that we're going to be using to think about this. So I don't remember how this particular story goes. There's a tortoise, there's a hare. The tortoise tends to be like really slow and deliberate and careful and patient, and the hare tends to sort of charge ahead directly to the goal, right? So you can probably imagine where we're going with this, but like the hare is going to be greedy search, greedy best first search. The tortoise is like uniform cost search from last time, because uniform cost search expands in every direction, always wants to make sure that it hasn't left anything out. And it will definitely find the optimal solution, but it might take a long time. So this is greedy. And then maybe we can think about this and say, like, is there a way that we can combine these two? Like, these two seem to be doing nice things, complementary things for us, right? The caution and the sort of the deliberateness of this tortoise is really nice to have, but if we could just push it in the direction of the goal, that would be really useful, right? So maybe we can achieve that. Right? So the tortoise is going to be looking out for what we should be paying attention to, and it should be like, helping us to be cautious and careful. And then the hare is going to make sure that the tortoise moves a little quicker. So that's the basic idea with A-star search. Okay. So let's just recap from last time. Uniform cost search first, which is also sometimes called Dijkstra's algorithm. I can't remember if we mentioned that last time. So if you've heard of Dijkstra's algorithm before, that's Dijkstra. It's just uniform cost search. And I'm just preparing my pen here so I can draw on our diagram, right? So we have this search graph, and there's a lot of numbers on here, so let's just look at them one by one. So these edges have costs, right? So this costs 1, this costs 3, right? So these edges take us from one state to another. Those are actions. The actions have costs. And then these h equals 6, h equals 5, those are the heuristic values for the state that they're next to. So the heuristics operate on states. The actions have costs. That's what all the numbers mean. All right, so we're going to do uniform cost search first. How does that work? Well, it starts the same way every time. We always add the starting state to our search tree. And uniform cost, how does it expand nodes that are in the frontier, in the fringe? So we add this state to our fringe, and then what node do we take off the fringe first? Well, it's easy because there's only one option, so we'll go quick here. So we expand that one, we put its successor onto the fringe, right? Then we expand that one, we put its successor onto the fringe. Now we have an option, right? So now there's 3 things we could choose between. How are we going to choose between these different nodes? Uniform cost search. Well, uniform cost search says pick the one with the lowest cost. We have to pick the ones with the lowest cost before we pick the ones with the higher costs. So the lowest cost here, if we're keeping track, we can go through. I'll use a different color. So to compute the cost of B, we have to go from S to A, that's 1, and then from A to B, that's 2, right? So that's why there's a 2 here. If we go to D, we have to go from S to A, that's 1, and then we go from A to D, that's 3, so that's why there's a 4. 3 plus 1 is 4. And same for E, we get a 9. Okay? So this is now our fringe in blue. So we're going to pick off we're going to pick off B first, right? We're going to add its successor to the tree. It only has one successor, it's node C. But now C is part of the fringe. I'll try and draw the fringe in another color. So now the fringe is in green. Hopefully folks can see the green. Right? That's our fringe. So what do we do first? Well, we pick off the one with the lowest cost. What's the lowest cost? It's C. Why is that the lowest cost? Because 1 to A, 1 to B, 1 to C, that's 3 total. So that's the lowest cost. So now we have to pick off C's successors. We pull C off of the fringe. Boom. Add C's successors. Does C have any successors? Well, I've sort of drawn over the lines, but the lines all have arrows, which suggests that C, you can only get from B to C. You can't get back. So C is a dead end. So our search terminates here. We're done. We've failed. Well, no, hold on. We didn't fail because we have more nodes in the fringe, right? So we pull C off the fringe. It doesn't have any successors. We go back to the fringe. We can just look at the next node. What's the next lowest cost? The next lowest cost is D. So we can pull that off the fringe. And so if we pull that off the fringe, we have to add D's successors, which is G. And hey, that's the goal. That's nice. So we found the goal. So now we're done. So the final path, I'll do it in yellow here, is S to A to D, D to G, and there we go. We're at the goal, right? So that's good. Uniform cost search. It finds the optimal plan. We get there eventually. But we have to do some searching over on the left-hand side in this corner and deal with B and C, and that's kind of frustrating because we're going in the wrong direction. But that's uniform cost search. It doesn't care what direction it goes in. Cost is most important. Questions on uniform cost search? Yeah.
So the program just terminates with the plan goal and continue looking down the fringe to see if there's a better path somewhere else.
Yeah, so hold that thought. We'll get into that in a minute. Great. Other questions? Yeah.
It's always optimal, right?
Uniform cost search?
Yeah.
I think that there are some conditions on that, but yeah, we're gonna get into when things are optimal later. Yeah.
I'm kind of like let's do the Pac-Man game and you put in difference.
Right.
And how like it kind of the Pac-Man like went another route.
Right.
Measured on the pretty distance. So I think if the cost is the distance, I think it wouldn't be optimal and you would need another measure of time.
That's exactly right. Yeah, so we'll look at what happens if we use the heuristic as our expansion criterion next. Okay? All right, so why don't we do that? Why don't we dive in? Let's compare uniform cost search, which only cares about cost, with greedy best first search, which only cares about our heuristic. Okay? So how does it start? It starts the same way. We always put the starting state onto our search tree, but notice that the label is now the heuristic and not the cost to getting to that node. So the cost is h equals 6 here. All right, so we put it on the fringe, we take it off the fringe, we put its successors on, we do this a couple steps, we get to this place where now we have a decision to make, right? B, D, and E. And what are the values associated with B, D, and E? Well, those are coming from the heuristic, right? So B is over here. It has a heuristic value of 6. D has a heuristic value of 2. And E has a heuristic value of 1. So greedy best first search doesn't care about the cost to getting to any of these nodes, right? It doesn't care about the cost at all. All it cares about, it's greedy. It says, can the heuristic improve or not? And so if the heuristic is low, we're going to expand that node first, right? So our frontier, our fringe, looks like this, right? It's all those 3 nodes. And the first one we're going to pull off is just the one with the lowest heuristic value, which is E. So we pull E off of our fringe. And what happens next? We put D on. Why is D appearing again in our search tree? Hopefully you guys are getting bored of this question now. D is appearing twice in our search tree because there's different ways to get to D, right? So now what does our frontier look like? It's B, D, and D again. There's 2 Ds, one because we've gone through E and one where we haven't. And we can now look at this heuristic as well. D still has the same heuristic. If we put a state in, we don't care about the path to reaching that state. We don't care about E being expensive to get to because E has a cost of 8 from A. We don't care about any of that stuff. Just the fact that it has a low heuristic says, oh, that's great. Let's go that way. Goal looks like it's that way. Let's go that way. And then we have a choice here between 2 values that have the same heuristic. Let's just assume, for the sake of things being interesting, that we pull the worst one off first, right? So we pull this second D off. And we get the goal. So now we see that there's this goal here. So we see a goal, and then we say, all right, that's a pretty low heuristic value. And yeah, we're done. We found the goal. Great. So greedy just says, let's go for the goal. Only worry about the heuristic. Uniform cost says, let's expand in every direction, make sure that we've crossed every T, dotted every I. We're going to make sure that we've been really careful and deliberate, but we might end up searching over in this section here unnecessarily. So maybe we can combine these 2 ideas together, put the tortoise on top of the hare, that kind of thing. So yeah, we talked about this. Uniform cost search orders by backwards cost, which is like the cost looking backwards from where you came from. How much did it cost me to get here? G. And that looks like this. It does some extra searching. Then there's also greedy search, which says, we're going to look forwards only. Don't care about how costly it was to get here. I just want to get to the goal as quickly as possible. And so then we get a suboptimal plan, and this isn't great either. We'd like to have optimal plans, but not have to waste our time. So we put them together, and A star search is the answer. We're just going to add the 2 heuristics together and minimize that. We'll see what that looks like in a second, but it's going to find the optimal plan, and it's going to do a little bit less just thrashing about in the wrong directions. Okay, so how does it work? We start with the same start state as always. Great. But now our score is F equals G plus H. G is 0 for the starting state. Why is that? Because it's a starting state, right? We haven't gone anywhere yet. It doesn't cost us anything to get there. Plus H, the heuristic, which is 6, right? So 6 is our heuristic. Where does that come from? Some function. We put a state in. The state tells us 6. The heuristic tells us 6. So we keep going. We expand. I'm just going to fast forward to when we have an interesting decision to make. And so our frontier looks like this. And now we're going to order nodes by this F cost, this F score. So the lowest one is going to win, right? So how does this B score arise? Well, it costs us 2 to get to B, 1, 2, plus 6 for being at B, versus D, which costs us 1 plus 3 is 4 plus 2 is 6, right? So that's this 6. And E would cost us 10. So now we are taking into account the fact that E has a good heuristic, 1, but it's pretty expensive to get to E from A. That's the 1 plus 8, or 9. Right? So the first one we're going to pull off of here is actually the middle one, is D, because that has the lowest total cost, this lowest F score. So A star just expands to the goal. So then we get this path, we see the goal, and then we're done. Great. So I keep saying we see the goal, we're done. I see the goal, we're done. Is that the time that we're really done? Like, are we sure about this? Someone asked the question. They didn't think maybe that was the best idea. Should we stop when we in-queue a goal? I don't know. Let's go through another example and see what could go wrong. We start with S, right? S is over here. That's our starting state. We always do this. We look at its successors, A and B. A has 2 plus 2 for being at A. There's a heuristic of 2 plus this 2. B has 2 plus 1. So which one are we going to expand first with A star? B. So we expand B, we get the goal. We've added the goal to our frontier, right? What our frontier looks like is this. This is our frontier. Are we done? We'll stare at this for a second. What does that correspond to? If we just say G, go SBG, what does that path correspond to? It's not the best path, is it? It's not the optimal plan. So we're not done yet if we want to find optimal plans. What should we look at? Well, we should just keep going. We still have this frontier. Why not use it, right? We have this expansion criterion, right? What do we expand first? 5 plus 0 or 2 plus 2? 2 plus 2. All right, so let's expand A. What happens? We expand A. We get another G. We put 2 G's into our search tree. Which G is better? The new one. So now our fringe looks like this. And now we have to continue our algorithm. We have to expand one of these 2 G's. Which one do we expand? 4 plus 0 or 5 plus 0? 4 plus 0. Great. So we expand this one. And now that we've expanded the goal, now that we've dequeued the goal, we've taken it out of the frontier, out of the fringe, now we can stop the search. Now we say, okay, now I have a goal. And by the way, this plan is optimal, right? Now I'm going over here. 2 plus 2 is 4. Check. Declare victory. We move on. That's great. So only stop when we dequeue a goal. Yes?
And you said why A star is going to find the optimal path and more optimal way than Dijkstra. But is there like a specific case where Dijkstra would actually be less wasteful than A star to find the optimal path?
So Dijkstra is a special case of A star, and we'll get into what that special case is later.
Is it possible for Dijkstra to be faster?
If your heuristic is leading you astray, it could potentially still help you. Yeah, we'll get into the specifics of what that looks like later, yeah.
So what if the heuristic for A was really bad in this case? Like let's say it was something like 5.
Yeah.
And then we got to the point where A and G were
Mhm.
both on the fringe. Like in that
We're going to look at that one right next slide. So let's do that. Any other questions before we move on? Yeah.
Both the S have ultimately the same sum.
If 2 paths have the same sum?
So S to A to B and S to B to B, they have the equal sum.
Well, let's look at the graph, right? The graph is the source of truth here, right? Well, technically the world is the source of truth, but this is our model of the problem. This is what we believe is the truth now. So we take this path, it takes us 2, then this path takes us 2. That's 4 total to get to the goal. Whereas if we took this path 2 plus 3, that's 5. So the blue path is definitely less. If you're adding up these numbers in the tree, these numbers are sort of like running estimates of what we think the cost is going to be. Yeah.
I was going to cover the pseudocode for this because I'm stuck how to like basically make that swapping.
Yeah, we'll have pseudocode at the end. I just don't want to take us through it because it takes a little while. Okay, yeah, one more question? In this case, uniform cost search, what's going to happen? I guess we would expand all things of cost 2, then we would expand all things of cost 3, there's nothing, 4, we'd get to the goal, and then yeah, we would see that first. So in this case, our heuristic kind of led us in the wrong direction. We had a lower heuristic value for a higher cost. So what's the same? Uniform cost search would have found the blue path first, and then the red path. They're both optimal, but they don't expand in the same order. Uniform cost search doesn't care about the heuristic at all. It just looks at the cost of getting to the state that I'm in. So it says, you know, I'm in A or I'm in B, and it just ignores the second piece, the H term. It just says 2 versus 2, right? Ignore this 2. It's the first 2, which is the G score, and then the first 2, which is also the G score. So it compares these two nodes. It breaks ties arbitrarily, so it might expand A or it might expand B. And depending on the order that you expand them in, you might see this G first or that G first. But let's say that you expand this one first. Then you have a 4, which has a 0 heuristic, but we don't care about the heuristic. We're just expanding cost. So 4 is the goal, and that's going to be less than this. So yeah, we'll expand all the nodes, but we'll get the optimal path. Yeah. Okay, let's do another example and prove when this will be optimal and when it won't be optimal. So here's a case where we have 3 nodes. We got rid of B, and we want to get to the goal. We want to see if A star is gonna find the optimal path for us. Let's do the same thing we always do. We put the starting state into our search tree. We expand to find its successors, and then we expand the frontier based on which one has the lowest F score, 1 plus 6 or 5 plus 0, right? 1 plus 6 or 5 plus being at the goal, which has a heuristic value of 0. So we're going to do the second one. And we're going to say that that's the goal. We expand the goal, and now we're done, right? So why did this go wrong? Why do people think that this might have gone wrong? Yeah. The heuristic values don't match with the costs. Well, the heuristic's an estimate. Why do I need the heuristic to be exactly matching the costs? Yeah, if it's a bad road and we say it's a good road, then we're going to go down the bad road first. And what happens here is that, like, so we try that. The actual bad road goal cost of 5 is less than the heuristic, the estimated goal cost on the good road. So our estimate says it's way too expensive to even look this way. Don't even bother. It's not worth it. It's hopeless. So we see this heuristic. Our heuristic is like really pessimistic. It's kind of depressing, that heuristic, right? Like I look at that heuristic and I just get sad. It's so bad. I don't even want to look over there. I'm just going to look at this path. This path looks fine, right? And so that's what happens, right? So we need to estimate that the path to the goal is going to be less than the actual cost. That way we'll be just optimistic enough to search everywhere, and we won't ever rule out things before we need to rule them out. So that's the concept here. So you can think of this as like an optimistic heuristic. Technically the word is admissible heuristic. So this is like we have kind of an optimistic machine here, an optimistic heuristic, versus a pessimistic machine that looks more like this. It says abandon hope, or it's still pretty bad. I don't know, just good luck, right? If your heuristic is always really pessimistic, then you're not going to look at most of the paths that are available to you. You're going to say, it's not worth my time. I'm not going to look over there. But if you have an optimistic heuristic, then you will say, it looks good enough. We could maybe take a look. And the sweet spot is somewhere that's not optimistic or pessimistic. It's exactly right. You know, you're not overestimating, you're not underestimating, but that's the exact heuristic. That's just the cost. And so that's kind of as hard as planning. So we're gonna, if we're gonna have an estimate and it's not gonna be perfect, we want to be on that side. We want to be on the positive, the optimistic side. We want admissible heuristics. So what that means formally is that a heuristic is admissible if it always underestimates the true cost. So the true cost is H star. It's like the best possible cost that we could estimate. That's why it has a star on it. It's the true cost of the nearest goal. And then the heuristic needs to always underestimate that or match it. And that's the property that we need to have. And we're only going to worry about non-negative heuristics. So it could be 0 if it's the goal, but it could be positive if it's not. And this is what it means to be admissible. So here's some examples of admissible heuristics. Pac-Man, right? So we had this Manhattan distance. That's an admissible heuristic. Why is that admissible? Because it doesn't take any walls into account, right? We still have to get to the goal. We have to get there from here. It's going to take us at least this many steps if there was no walls, but there's walls. So we have to go around. It's going to take us more than 15. So 15 is an underestimate. We can look at the pancake problem too. Remember we had this heuristic of like, what's the index of the largest pancake we still need to flip? And if the index is 4, then our heuristic says 4. But if you think this through, there's actually a way that you could probably flip this stack in 2 steps. I think if you just flip the whole thing, you put the big one on the bottom, and then you flip these 3 once they're on the top, and then you would solve it in 2 steps. So this heuristic is overestimating, so it's not admissible. And coming up with an admissible heuristic is often most of what's involved in using A star in practice. So this is kind of an art form to coming up with admissible heuristics. Okay, yeah.
Like the first one would actually be a good one for A star, right?
Yeah, this one is optimistic. It says I can get there in 15 steps. I don't care about walls. And then this one says, oh, that's a pretty big pancake. I don't know, it looks pretty tough to me. I'm pessimistic. This seems like it's going to be hard, when it's not. So that's not admissible. Yeah. Okay? Yep.
Just out of curiosity, is there a heuristic known for this pancake problem that would be admissible?
I'm going to leave that up to you to think about. Let's move on. So because I really want to prove to you that A star is optimal. And if we can prove that, that would be pretty sweet, right? Because we really want this property. We want to make sure that we're always going to get optimal search. How are we going to get there? Well, there's a couple of steps. Let's visualize this search tree, right? And so basically, we're going to make some assumptions about A star. We have this admissible heuristic. Let's say A star with an admissible heuristic is enough for us to have optimal tree search. We're going to always find the optimal plan. Well, when would we not find the optimal plan? We would have to have at least 2 goal-achieving plans, and one of them has to be worse than the other. If we only have one, we're going to find it because this thing is exhaustive. It's going to try everything. Eventually, we will get to the goal. But when we get to the goal, if it's a bad goal, like B, which is farther away from the starting state, that's not what we want. That's not optimal. We want to get the shortest path to the shortest goal, right? So A, we're going to assume for the sake of argument that A is better than B. A is shorter path than B. So I'm going to claim that if we have this heuristic that is admissible, and A is an optimal goal node, and B is a suboptimal goal node, I'm going to claim that A will always exit the fringe before B. How could I make this claim? Well, let me try to prove it to you, okay? So the first step of the proof is like this. Imagine B is on the fringe. If B is not on the fringe, then there's kind of no danger yet. We have to either, if nothing's on the fringe, then we're okay. We haven't terminated the algorithm yet. If A is on the fringe, then we can always just take A off. So I'm not really concerned about that either. The real problem issue comes when B is on the fringe and A is not on the fringe, right? Now I'm scared, right? Because you can think about this as like the search is proceeding in 2 directions, right? The search is proceeding down the left side of the tree. The search is proceeding down the right side of the tree. It's like a race. The left side needs to get to A before the right side gets to B. If the right side gets to B and then we terminate the search and declare victory, then we have a suboptimal plan, just like greedy search found. So that's what we want to try to avoid. So we want to make sure that this race, that A is always going to win in this race. And right now I'm scared because B is like within reach, It's in the fringe. It's already on our fringe. And so like how do I show you that we're still going to pull A off the fringe first? Well, the trick, the insight is that if we're in this situation, there is a node that is like an ancestor of A on the path to get from the start state to A. That's an optimal path that must be on the fringe, okay? So we can put that node on here. It might be A. Maybe it's actually A. It might be the start node, but there's definitely a node in between that is on the optimal path from the start node to the node A, and we're just going to call that node N, and it has to be on the fringe. Why does it have to be on the fringe? Because we haven't expanded everything yet, so there must still be a path to the goal. So we haven't terminated the search yet, so anything that we can still reach is either on the fringe or it has an ancestor on the fringe. So we just think about this node N, okay? And what can we do now that we have this concept of the node N? The claim is that N will be expanded before B, so there's nothing to worry about. This node that's on the left side of the race is going to beat out this node on the right side of the race, and so we're still going to be okay. N is going to be expanded before B. Okay, how could we do that? Well, which nodes get expanded, right? Like if we have this fringe, right? We have this fringe. Which nodes get expanded first? A star says we need a lower score. We need a lower score. Which score? The F score, G plus H. So the cost to getting to the node N plus the cost from N to the closest goal that's to N, right? And same for B. So that F score for N has to be lower than this F score for B in order for us to pull it off first. But that's hard to think about, comparing N and B. So first let's think about this comparison. This will be an easier thing for us to compare. We're going to compare the F scores for N with the F score for A. And I'm going to claim that the F score for N is less than the F score for, or less than or equal to the F score for A. Why is that the case? Well, F is less than or equal to, F of N is less than or equal to F of A. Well, we could just write down the definitions for F, right? F is this G plus H. G is the cost of getting to the node. H is the cost that we're estimating from that node to the goal. So for N and A, we know that N is on the optimal path to A. We know that A is the optimal goal. And so the H cost is this estimated cost of getting from N to A or A to A. A to A. What's the estimated cost of getting from A to A? 0, right? Because why is that? Because we have what kind of heuristic? It's admissible. So if it's always underestimating the cost of getting to the goal and the true cost of getting from A to itself is 0, how do we underestimate the true cost with a non-negative number? There's only one option. We have to choose 0. So that's the only underestimate of 0 that is a non-negative heuristic. So we know that that's 0. We can cancel it out of these two expressions. And now we have a simpler one on the bottom, right? So we have F of N is the path that gets to N plus the estimated cost from N to A. And then we compare that with just the cost of getting to A, this blue part, the G. Okay? So I'm going to claim that H of N must be an underestimate of the true cost from N to A because it's an admissible heuristic, which means that the total path cost, which is the path to N, which I'll put in red here, plus the path from N to A, has to be less than what I'll put in blue, which is this straight path just going directly to A, right? That has to be an underestimate because the heuristic part is underestimating. The rest of it is the same. The actual cost of getting from the start to N is the same. N is on the path to A. So this has to be an underestimate. So that means we add these two terms together. F of N is less than F of A. Okay, but I didn't ask about F of N versus F of A. I asked about F of N and F of B. So I'm trying to claim that F of N gets pulled off the fringe before F of B. Or rather, the F of N is less than F of B, right? So N gets pulled off before B. So that's still confusing to me. Like, I still can't think about N versus B. But let's think about A versus B. Maybe that'll be easier, right? So I'm going to claim that A has a lower F score than B. Why is that? Well, let's start with the definition of this F-score again. We can put down the F-score for both nodes. A is the path to A plus the heuristic from A. B is the path to B plus the heuristic from B. We can cancel these terms out. Now we can cancel both, because it's A to A and B to B, which are both 0. The estimate has to be admissible, so it's got to be 0 for both of them. So we cancel those out. The red parts go away. And now F just equals G. What can we do now? What do we know about A and B? A is better, right? So A must have a lower cost of getting to A than B has getting to B, right? So because we assumed B was suboptimal, we know that now G of A is less than G of B, which means F of A is less than F of B. So back to here. The last step is if N is less than A and A is less than B, then N is less than B. So that means that N, this node that is in A's ancestry, will always expand before B when they're both on the fringe. And that's going to be true for every ancestor of A until we get to A. And then when we get to A, we already know from step 2 that F of A is less than F of B, so we'll still expand A first. All ancestors of A expand before B. A expands before B. A star is optimal. Yes? So B can be on the fringe before A. And this diagram shows what happens if that's true. It might be the case that B gets put onto the fringe first, but we don't stop the search when we put a goal node onto the fringe. We only stop the search when we pull a goal node off of the fringe. Yes, dequeuing, yes. Yeah, so when we inqueue B, we don't stop the search there. We wait until it's time to dequeue B. Yes? When do we ever dequeue something from the fringe? When it's the lowest of whatever our expansion criteria is. So if we're expanding uniform cost search, it's the one with the lowest cost. If we're expanding greedy best first search, it's the one with the lowest heuristic. And if we're doing A star, we have to do the lowest F score. Yeah, so this works for more than one goal node also, because you're always going to expand the N node before, let's say you have B and C are both on your fringe. Well, N is still, if A is the best goal node, then N is still going to have a lower F score than B or C or D or E. So it's just you add nodes to your fringe based on when you expand previous nodes, and you add their successors, and then you add all their successors to the fringe, and then just the lowest F score node that's on the fringe is the one that you expand first. And so that's always going to end up being N first, and then the ones over by B and C are going to happen later, but we'll have found A by that point. I'm gonna throw this up there. That was a lot of proof. Let's just take a quick breather. We'll do the attendance code. Today's code is flapjacks, which is another name for pancakes, if folks don't know that. Okay, hopefully a few folks were able to scan that at the beginning, so I'll give you another, let's say, 15 seconds. And this code, just write down the code if you didn't have time. And the link is on the website still. So if you ever can't scan the code, you can just go to the website. All right, so let's look at what this looks like in one of these maze environments. Turn the pen off here. Right, here's the empty maze. So uniform cost search, remember, it expands in every direction. So that looks like this. Eventually it finds the optimal path. That's great. Here's greedy. Remember, greedy goes directly there. It's also great for an empty maze, but if there's walls, we had problems, remember? And here's what A star looks like, right? So here's the maze. A star is going to expand a little bit in every direction for the low-cost stuff, but only if it seems like it's plausible that it could lead to a good plan. So that looks like this. So we have a really nice shape. We have this sort of circular region where we're expanding in all directions for cheap stuff, and then we have sort of focused exploration in the direction of the goal. That's what A star ends up doing. Okay, I'm going to skip through some of these applications, but here they are. There are tons and tons of applications of A star. I want to talk about creating heuristics. So I said this before, but most of the work in solving hard search problems is in coming up with good heuristics. How can we do that? Well, often these heuristics end up being solutions to these relaxed problems. I said this earlier. What does it mean to be a relaxed problem? It means that it's not as hard as the first problem. So in the problem where we're navigating from Arad to Bucharest, a relaxed problem says you don't have to stay on the roads. You can fly. Okay? There's still going to be some distance, but a relaxed version of the problem says don't worry about roads, don't worry about stopping for gas, don't worry about trees or mountains or any of that stuff. Like you can just go directly through it. Maybe you've installed cheat codes on your world, right? And now you can just go directly to the goal. That's a relaxed problem. Another relaxed problem says Pac-Man can tunnel through walls. Pac-Man doesn't have that superpower normally. It might be fun if he could, but tunneling through walls would make this a much easier game, and so that's a relaxed problem. We can come up with heuristics by thinking about relaxed problems. Inadmissible heuristics are often useful too if we don't care about optimal plans. I'll just say that, sort of something else to think about. But here's another example. This is also not a 2D navigation problem. Who's played this puzzle before? This is like a sliding tiles puzzle. It's called the 8 puzzle. They also have a 15 puzzle and they keep going up, 4x4, 5x5. They get really complicated when you have more than about this many, or 15 is like kind of the upper limit. There's just, how many states are there in this problem? Do we know? So yeah, let's just think about, so in the top left corner, right, there's this state, or this tile. There's 9 values that could be, times 8 values for the next one, times 7 values for the next one. You see where this is going, right? And then there's 1 for the last one because it's kind of determined by the first 8. So this is like 9 factorial. Technically it's 9 factorial divided by 2 because there's like a parity thing. There's certain configurations that you can actually get to and certain ones that you can't. But that's a lot of states. And if you had more tiles, if you had, you could actually put this in memory, but if you had a 4x4 or a 5x5 or, God forbid, a 6x6, this would be just so many that you wouldn't even be able to fit them in memory. What are the actions? We can move the tiles that are adjacent to the empty square. So 6, 5, 2, 3, we can move those into the empty square, and that causes a new configuration. That's a new state. How many successors from the start state? Well, there's just those 4. But from other states, like from this state, which is actually the goal state, there's 2 successors. There's 1 could move into the space, and 3 could move in. So there's not the same number of actions in every state. So the heuristic that we're going to start with is the number of tiles that are out of place. Why is this a good heuristic? First of all, what is it? Like, how many tiles are out of place here? Well, actually, none of them match, right? 7 doesn't match blank, 2 doesn't match 1, 4 doesn't match 2. All 8 tiles are out of place. So the heuristic for this state, the starting state, would be 8. Why is this an admissible heuristic? Well, one way to think about it is that it's solving a relaxed problem. It's saying the relaxed problem is that I can move any one of these tiles directly to where it needs to go in exactly 1 move. And that's a lot easier than, what is that? That's actually just cheating, right? It's like you pull the thing out of the board, you put it where it needs to go. That's a much easier problem to solve than the one where you have to move them around carefully and obey the rules. But nevertheless, this is a good heuristic, and if you use this heuristic versus uniform cost search, once the problem starts to get really big, you go from millions of nodes expanded to 200. So this is a really big cost savings. Here's another heuristic we could look at. We could use the Manhattan distance for each tile. So just imagining that every tile, let's say the 7 tile again, can move where it needs to go by following the shortest Manhattan path to get there. So this is going to be a higher number than the previous one, where it took us 1 step to move 7. Now it's going to take us 3 steps to move 7. But this is a different problem. This is like a different relaxed problem. This is a different heuristic. So the total Manhattan distance, why is this admissible? Because it's going to take us at least 3 steps to move 7 there if we didn't have to worry about these tiles being in the way. But of course the tiles are in the way, so it's going to be definitely at least that distance. So we could add up all the heuristics for each of these tiles, and that would give us 18 for the starting state. I won't go into the details, but this will give us an even further reduction in the amount of nodes that we expanded. So we get 200 versus 73, and so this is even nicer. Someone asked earlier, what if we just used the actual cost as our heuristic? It would be admissible, right? Because it's an underestimate of the true cost. It's less than or equal to the true cost. It'll save us on nodes expanded. Yeah, it'll save us. We don't expand anything except the optimal plan at that point. So that's kind of nice. If it's on the optimal plan, we'll expand it. If it's not, we won't. But the thing that's problematic about this is that we have to do a lot of work to come up with the exact heuristic. We have to actually solve the planning problem to come up with the exact heuristic. And we can't solve the planning problem in finding the heuristic that we're going to use to solve the planning problem. That just doesn't work. So there's this trade-off. There's some spectrum between good heuristics and bad heuristics, and we want to try and find ones that are a small amount of work for us to use to estimate, but that are not too expensive, and that'll still be reasonably good for directing our search. I'll just say this real quick, which is that if you have multiple heuristics, you can compare the quality of them. So maybe you have, on one end, you have the exact heuristic. That's like the best you could find. That's impractical. We can't find that. On the other end is 0. It's just a heuristic that you give it any state and it says it costs 0. That's always going to underestimate the cost of getting to the goal because it's always saying 0. So that's a valid heuristic. It's kind of the worst quality heuristic, but it's technically a heuristic. And if it's admissible, because it always underestimates, then it technically satisfies all of our proofs of like A star being optimal. And this corresponds to this. So if we use the 0 heuristic, then that corresponds to uniform cost search. It just says ignore the heuristic. Just worry about the cost. So on one end here is uniform cost search. So now I've just proved to you that that's optimal as well. And then above that, we have some better heuristics. Imagine this is like the number of tiles out of place heuristic. And this one is the Manhattan distance. And we say that a heuristic dominates another heuristic if it's always bigger than that heuristic. So this is saying it's always going to overestimate the first heuristic, but still underestimate the true cost. Yeah, so we might have 2 heuristics where that's the case for every state. We'll say that's what dominance is the heuristic is always bigger than another heuristic. That means it's always more accurate. Our estimate's better. But it could be the case that we don't know how to compare A and B to each other, and so there might be no relationship. For some states, A says it's more steps to the goal. For those same states, B says it's less. And then there's some other states which the reverse. But we can always just take the maximum of 2 heuristics. This is kind of like a fun little trick. And the maximum of 2 admissible heuristics has to be admissible. So that's like a quick and an easy trick. You can just make an admissible heuristic out of 2 other admissible heuristics. Looks like we're running short on time. So graph search we will cover real quick next time. And then we will get into the next unit, which is games.